Welcome back, everyone. In today's lecture, we will discuss perfectly secret encryption. So, if you want to read up on the materials covered in this chapter, I'll refer you to chapter 2 in the book of Katz and Lindell or chapter 2.2 in the book of Bonnet and Shoup. Let's briefly consider today's materials in a historical context. Until World War II, the design principles of ciphers were military secrets and not subject to open research. During World War II, especially the Allies recruited many civil mathematicians and engineers in their cryptanalytic efforts. During that time, it was realized that the central weaknesses of contemporary ciphers was that ciphertext preserved certain properties or invariants of plaintext. For instance, for the substitution cipher, we saw that the ordered histogram of character frequencies is preserved. Or a flaw of the enigma was that we can rule out that a ciphertext encrypts a certain message. After World War II, we saw the beginning of the information age. In science, this was reflected by the seminal works of Claude Shannon in 1948 and 1949 in information theory, the latter of which marking the birth of modern cryptography. We will now provide a formal definition of what constitutes an encryption scheme, also called a cipher. What we provide here is not the full definition, but a simplified notion called Shannon cipher. The full definition will follow in the lecture on symmetric key encryption. We will first talk about syntax, that is, the algorithms that comprise an encryption scheme and a property called correctness. An encryption scheme consists of three algorithms, keygen, enc, and dec, and three sets k, m, and c. We call the set k the key space, the set m the message space, and the set c the ciphertext space. The keygen algorithm is a randomized algorithm which outputs a key k in the key space. So we say the keygen algorithm is a randomized algorithm, which means that it takes uniformly random coins as input. Thus, we can see the keygen algorithm as a sampling algorithm for keys. Usually, we don't explicitly mention the random coins, but keep in mind that keygen is a randomized algorithm, and each invocation of this algorithm uses fresh random coins. The enc algorithm takes as input a key k and a message m, and outputs a ciphertext c. Typically, enc is also allowed to be a randomized algorithm, meaning that it can consume random coins. The dec algorithm is a deterministic algorithm which takes as input a key k and a ciphertext c and outputs a message m. We need to ensure that the algorithms of an encryption scheme do what we expect from them in terms of functionality. Namely, decrypting ciphertexts yields the correct plaintext. We call this property of an encryption scheme correctness. An encryption scheme without correctness is useless, as we encrypt messages in order to decrypt them later. So, we say that an encryption scheme is correct if it holds for all messages m in the message space, that if we first encrypt the message m with a key k and then decrypt it with the same with the same key, then we obtain back the message m, where k was obtained by invoking the keygen algorithm. But wait, both keygen and enc are randomized algorithm. So the statement we defined up here is actually an event. That means the correct requirement for correctness is that if k is chosen by keygen, now this means k is a random variable, then the probability that first encrypting with k and then decrypting with k gives back the same message m is 1. Note that this probability is taken over all random choices in the sample space, namely over the random choice of k, that means the random coins of keygen, and the random coins of the enc algorithm. Now let's turn to the problem of defining security. How should we go for this? Looking back to the lessons we've learned from historical ciphers, we want that if you see a ciphertext, you shouldn't learn anything about the message it encrypts. In the last lecture, we've seen the concept of independence of random variables. And this was Shannon's idea for defining perfect secrecy or perfect security. The ciphertext, as a random variable, should be independent of the message as a random variable. So clearly, the ciphertext is a random variable, but what about the message? What should the distribution of the message be? And the answer is any distribution. We don't know the context information of the adversary, so if we say that the distribution of the message could be anything, then we will err on the conservative side. So here's our first attempt at defining security of a cipher, called perfect secrecy. Say that an encryption scheme keygen encdec is perfectly secret if it holds for any random variable m supported on the message space that m and a ciphertext c, which is an encryption of m, are independent, where the key k is chosen by the keygen algorithm. Note that the ciphertext capital C is a random variable which depends on the other random variables k, namely the key, and m, the message. Writing this more formally, we require that it holds for all messages m in the message space and every ciphertext c, which has positive probability of being the output of encrypting a message chosen by m, that the conditional probability of the message m being lowercase n, given that the ciphertext is c, is the same as m being m unconditionally. One additional comment maybe: in the future, when we condition on events, we will implicitly assume that the event which we condition on has non-zero probability and not explicitly state this as we did it here. So now that we have definitions of syntax, correctness, and security for a cipher, let's see a cipher which actually achieves our security notion of perfect secrecy, the one-time pad. For this cipher, the key space, message space, and ciphertext space are all the same, namely binary strings of length m. The keygen algorithm just chooses a uniformly random string from 0, 1 to the n and sets this to be the key. Encryption takes as input a key k, message m, and basically XORs the key k onto the message m. And decryption does the same thing. It takes a key k and a ciphertext c and just XORs the key k onto the ciphertext c. Note immediately that here, as we've just stated, keys are as long as messages. A quick historical note maybe: the one-time pad is also called the Vernam cipher and was originally proposed by Vernam in 1917. What you see here is a modern description of this scheme. Correctness follows essentially directly. If we want to do this real quickly, let's check this. When we compute dec k of enc k of a message m, well, this is just k XOR k XOR m, and k XOR k, this is just the all zero string. So this is m. And we don't need to bother about the random choice of k. This event holds for any choice of k. So now let's move on to the slightly more involved task of proving that the one-time pad is perfectly secret. First, recall the simple observation from the last lecture about uniform distributions in groups. Since our key k is uniformly random in 0, 1 to the n, and recall that 0, 1 to the n with the operation XOR is a group, then k XOR m for any message m in 0, 1 to the m is also uniformly random. Moreover, if we take any distribution of or any random variable m, which is supported on the message space, and know that m and k are independent, or and k independent. No. Independent. Then it also holds that m XOR k, or k XOR m, is distributed uniformly random. So, what do we have to do to show that a cipher is perfectly secret? Well, we have to show that messages distributed according to any distribution m. Now, fix any distribution m. We have to show that for all messages lowercase m and ciphertext c, it holds that the probability of m equals m conditioned on encryption of m being c is the same as probability of m equals lowercase m. So let's compute this conditional probability. So probability of m equals m conditioned on enc k of m equals c. Well, let's first plug in the definition of our encryption algorithm. This simplifies things already a little bit. This is the same as probability m equals m conditioned on k XOR m equals c. And when we see such conditional probabilities and it's not immediately clear what to do with them, a good guess is just to throw base rule at this. So let's do this. Applying base rule, we obtain that this is the same as probability that m, or that k XOR m equals c conditioned on m equals m. This already looks a lot better. The conditional probability the other way around. But base rule, we have these additional two factors, namely probability times probability m equals m. That's the one we want in the end, divided by probability of kx or m equals c. So this one here is actually quite simple. What does it mean when we condition on m being m? Well, we know k and m are independent, so we can write this first as probability kx or lowercase m equals c, because we condition on capital M being lowercase m, so we can just substitute capital M for lowercase m, and now here we have m equals m, but I just said that k and m are independent, so we know this is the same as probability kx or m equals c. But again, we know that k is chosen uniformly random and m is fixed now, so this is just 1 over 2 to the n, or 1 over the group size. So computing that one here is easy. Now what remains to do is computing this term here. For that, I'm gonna go to the next slide. So we wanna compute the term that is in the denominator, namely probability that kx or m equals c. What's this term? And as is very, very often the case, the term that arises in the denominator after an application of base rule, we could try to compute this with the law of total probability, and this essentially works most of the time. So let's do this. Writing this out, we make a summation over all messages m and take the probability of kx or m equals c conditioned on m equals m. Let's call this m prime because we had already a variable called m times probability m equals m prime. So what's this probability? Well, we can now just substitute m on the left side for m prime, and then observe that k and m are independent. So this is just probability of kx or m prime equals c. But we know since k is chosen uniformly random in a group, this is just 1 over 2 to the n. So this expression simplifies to 1 over 2 to the n times sum over all messages m prime, probability m equals m prime. But this sum goes over all messages m, so these events m equals m prime, they cover the entire sample space, and therefore this probability is 1. So altogether, this probability is 1 over 2 to the n. So putting things back together, we get that probability of m equals m conditioned on k x or m equals c is just, well, 1 over 2 to the n divided by 1 over 2 to the n. Nicely, that cancels out, times probability of m equals m. And that's exactly what we wanted to show. This is probability m equals m. So we have shown that the requirement for perfect secrecy is satisfied for all choices of the message M and the ciphertext C, and this concludes our proof. If we look at both the construction and the proofs of correctness and security for the one-time pad, we immediately observe that this construction doesn't just work for the group of binary strings with XOR, but in fact for any finite group. So we can set key space K, message space M, and ciphertext space C to be just a group G. Then our keygen algorithm becomes choosing a key K uniformly random from the group, and encryption is performed by just applying the group operation on K and M. Decryption is now performed by by multiplying K inverse onto C. Really, both correctness and security proofs are essentially the same as for the basic XOR one-time pad that we've just seen. So why is the one-time pad called one-time pad? As I've mentioned, it was invented by Vernam in 1917, who also gave it this name, one-time pad. But it was actually only proven secure under this definition by Claude Shannon in 1949. This is not 1948, but 1949. Before that, we just saw there actually was no formal definition of security for encryption schemes. Now note that the proof of security only holds if the key is used at most once. And if you look at this construction, it kind of becomes clear that if you were to use the key many times, then this would in fact become a variant of the Vigenère cipher. What this means is you cannot reuse the key. You can only use the key once, but that means that the one-time pad, if you were to really use it in a practical application, consumes enormous amounts of key material. The obvious question is, can we do better? Can we build perfectly secret encryption that where the keys are maybe much shorter than the message and the keys can be reused? To sum up this lecture, we've introduced the syntax of encryption schemes, namely the algorithms it comprises, and defined the notion of correctness. And I remind you, without correctness, encryption schemes are essentially useless, because if you have a scheme that's not correct, then encrypting a message amounts to the same as just throwing the message away. Such a scheme is essentially useless. We provide a Shannon's definition of perfect secrecy, which captures the intuition that ciphertexts should reveal no information about the plaintext. And finally, we showed that the one-time pad is a perfectly secure encryption scheme in the sense of Shannon. Thanks, that's all, and bye.